What you see in front of you is one example of a vertical asymptote. But why is it a vertical asymptote? Is it because the function splits around it, going up on the left-hand side and down on the right-hand side? Well, probably you know that is not the reason. For instance, this is also a vertical asymptote, and yet the function goes up on both sides. Is it because the function is actually getting close and closer to this line? Well, how do we even know it's getting closer and closer to that line? Is it because it's not touching the line? So, for instance, is this an asymptote or not? Well, that's what we're going to be discussing today. In fact, I want to start from this last concept, the whole idea of touching the asymptote, because that's a very common but incorrect idea. Let's see how that goes. So what's a vertical asymptote? Well, here is a definition which I found on the web, and I'm pointing this one out so that you can check it, but not because this is particularly unusual. This definition maybe in different words can be found all over the place. And this place they say that an asymptote is essentially a line. True enough, an asymptote is a line, although as you may discover in further courses, you can talk also about asymptotic parabolas and all kinds of other things. But when we talk about asymptotes, we're talking about a line. So far so good. That the graph approaches, yes, that idea is there. In fact, that's going to be the key idea. The function and this line is going to get closer and closer. But the problem comes when people want to add this last clause, but does not intersect. In fact, this last condition is a good one for an introductory definition. It sort of focuses on one of the things that we want to see, but is not really correct. And so what I would like you to do is think about this additional condition and realize that it is not really part of the definition of an asymptote. Because in fact, asymptotes are not about intersections. They have nothing to do with intersections. The lack of intersections between a graph and one of its asymptotes is something that we will in fact see very often, but it is really not crucial. It does not have to happen. In fact, in some situations it does not. What asymptotes are all about is limits. So let's see what a vertical asymptote really is. So let's have a look at the correct definition of an asymptote. So we're going to say that a function f of x has a vertical asymptote at x equals c. Well, if it's got to be a vertical asymptote, it better be a vertical line, and vertical lines are always of the form x equals some number. Oh, by the way, in this particular class, we're focusing on vertical asymptotes. In the next one, we'll look at horizontal asymptotes. There is also something called slant or oblique asymptotes, and we're not going to look at them in this course, but the idea is still the same, and you may want to discover those on your own. But going back to our definition here, so a function f of x has a vertical asymptote at x equals c if one of these conditions occurs. So which ones are these conditions? There's 4 of them, and only one of them will guarantee the existence of a vertical asymptote. The first one is that the limit as x approaches this particular value c from the left of the function is going to be infinite. So we're dealing with a situation where we have an infinite limit. The graph will look something like this. So we have the vertical line at x equals c, and as we're approaching from the left, the function will go up and up and up without any limit. Or the function may actually go down and down and down without any limit. So in this situation, we're going to see that the limit as x approaches c from the left-hand side still of the function is going to go to negative infinity. So once again, as the graph approaches the vertical line x equals c from the left, the function itself will go to negative infinity. Or the same thing, or one of these two conditions can hold on the other side. So we can have that the limit as x approaches c from the right-hand side is going to be infinite. So as we approach from the right, the function will go up, or maybe it's going to go down. Notice that one of these conditions is enough to let us conclude that we have a vertical asymptote. We don't need a combination of them. We don't need anything about intersections. It's just any one of these conditions will tell us that the vertical line x equals c is a vertical asymptote. And by the way, yes, you can have any combination of situation on the left-hand side with one on the right-hand side. So the function may go up from both sides, may go down from both sides, may go up from one side, down from the other side. It doesn't matter. In fact, it may even just go up or down from one side only, and from the other side there may be something totally different happening. So remember, only one of these conditions will guarantee the existence of the vertical asymptote. So when do asymptotes usually occur? Well, most often you're going to see asymptotes in connection with fractions. What do I mean by that? What I mean is that as you're trying to compute the limit as x approaches c from the left or the right of your function, you're going to end up with a situation where when you try to compute the function at c, you will come up with a fraction which will have on the top a number which is not equal to 0 and on the bottom the number 0. So in that situation, again, the function will look something like this. And why does that happen? Well, because in the function we have a small denominator. Small denominators make for large fractions. And in fact, because the denominator is so small that we can make it go to 0, the fraction itself can become as large as we want, and therefore will go to either positive infinity or negative infinity. One way to try and remember this situation is what I call my law of balloons. What do I mean by that? Well, we're dealing with a situation where we have a very light bottom. Okay, so we are dealing with a fraction. The bottom is very, very light. It's very, very small. And so you can think of that small light denominator as making the whole function float up into the sky. So you can think of this as a balloon that keeps going up and up and up and up, pushed by that denominator, which is becoming smaller and smaller and smaller. And now you might object to the fact that, okay, that's fine when the asymptote occurs because the function goes to positive infinity, but what about the other side? Well, remember, we are in Canada here. If you're watching from the United States, hello, it's very cool up here. But we have friends down in Australia, right? So what are those guys in Australia going to see? Well, they're going to see the balloons upside down, right? And so these things are still going to go up and up and up and up. Okay, it's an analogy. If it works for you, fine. If it doesn't work, don't worry about it. You may be able to find a better analogy that works for you. The key point I'm trying to make here is that these vertical asymptotes occur very frequently with situations where you have a fraction, a finite number on top which is not 0, and a 0 in the bottom. However, they do not always occur in this way. They can occur differently. We have already seen one example of that with the function f of x equal ln x, which is not a fraction but still has a vertical asymptote, and we're going to see some more. So what about intersections? I mentioned that the lack of intersections is often presented as one of the conditions for the existence of an asymptote, but doesn't have to be. In fact, it has nothing to do with intersections. Now, what is true, however, is that in most of the cases that you will see, we're going to be dealing with functions which are fairly simple, and therefore for vertical asymptotes, actually it will be true that the function will not touch its vertical asymptote. But that's just because we're dealing with fairly simple cases where we're going to try and avoid complications. Okay? But it doesn't have to be. Okay? A function can touch its vertical asymptote, and the easiest way to do that is by using piecewise functions. For instance, let's have a look at this particular function. It's a piecewise function defined as follows. Very simple one. It's equal to 1 if x is less than or equal to 1. So that means that the graph of the function to the left of 1 and up to 1 will be constantly at 1. Notice that at x equal 1, the function is defined, it is equal to 1, so there is a solid dot in there. But the function is going to be defined by 1 over x minus 1 if x is greater than 1. Okay? So this is still a function, a very well defined function, no problem with it. And now let's have a look at the line x equal 1. Now, I claim that the line x equal 1 is a vertical asymptote, even though, as you can see, the function does touch it, does intersect it. Why can I say that this is a vertical asymptote? Well, I'm going to use the definition. I'm going to look at the limit as x approaches 1 from the right hand side of my function. Remember, this is one of the conditions that I need to have satisfied in order to have a vertical asymptote. Is this limit infinite? Well, if I'm approaching 1 from the right hand side, I need to use the second formula for the function. So I'm actually computing the limit as x approaches 1 from the right, of 1 over x minus 1. And this is exactly a situation where the top is a finite number not equal to 0, it's 1, and the bottom is a number which is approaching 0, and therefore it's becoming smaller and smaller. The whole fraction is becoming bigger and bigger, and because I'm using numbers greater than 1, everything is positive, and therefore the limit is going to be positive infinity. That's what I need for a vertical asymptote. It's enough for it to be an asymptote on one side. On the other side, we don't care. So once again, remember the key important thing about vertical asymptotes, they are about limits.